I just want to make it very clear. If we use concentration like yesterday, the shape of the graph is the same. Whether you use concentration amount like moles. So if we have a graph of mole against time, what will the graph look like? Let's do my favorite. My favorite is the Haber-Bosch process. So let's do the Haber-Bosch process. 3 hydrogens and nitrogen will give you 2 NH3. Okay. So what will happen? We start with high moles of hydrogen and nitrogen. Am I right? So as the hydrogen and the nitrogen is being used up, the reaction will slow down. So the curve flattens out. What does it mean when the curve flattens out? When the curve is flat, what does it mean?
It doesn't change.
The gradient of the tangent doesn't change. So what does this flat part mean? The reaction has stopped. And I'm going slow here because we're still going to do reversible reactions with equilibrium, and then you're going to be confused if the graph goes flat and I tell you the reaction hasn't stopped. So with a rate graph, the moment the rate graph has flattened out, the reaction has stopped. Okay? A rate time graph. We start with a high rate. The gradient of the tangent to the graph, to the curve, is steep. And as we go along with the reaction, the rate of the reaction slows down. You can see the gradient is less and less steep as it reaches the end of the reaction. You are clear on that?
Wait, so then what does that like the curve mean when it's really...
The curve is how the moles change as the time goes along. So it is how many moles there are in that at that moment in time. Okay. The trick here is to understand, yes?
What's the difference between this and the concentration?
It's just will be the values on the axis.
So they have the same shape?
They have the same shape. They will just be represented by different values.
Yes.
Okay. So the problem here is to understand that if we look at the rate of the reaction and we want to calculate it, we must take the negative mole change. The negative change in mole over time.
And I have a question to ask. Why does the graph never reach zero?
Okay, let me draw the graph that reaches zero. Let me draw the rate graph. Let me just answer her question now. Here, the rate is the gradient. The gradient of the mole time graph gives you the rate. Are you with me? You get a rate graph where if I use this gradient, it will be there. If I use this gradient, it will be there. Sorry, not there. There. If I use that gradient, it will be there. So this graph goes down to zero. Sorry. my curves are not perfect here. Just get my curve right. So this, although the graph has the same shape, it's got a different meaning. This is a rate graph, and there the rate decreases to 0. So here the reaction has stopped.
Oh, so the zero on the race graph is the
Here the gradient is 0.
Because it will have same x values.
The time values will be the same, but the physical value on the y-axis will be different. I am.
So now you see how it doesn't end at 0 on the first one, right?
So this point here, let me just make it clear. This point there is the rate there. This point there is the rate at that time. This point here is the rate there.
Okay.
So here the gradient is the rate because it's a mole time graph. Here it's a rate time graph. So you take those gradient values and you plot them against time. The shape, unfortunately, is the same.
Now the question is, right? You see how the first one, the reason why it's not touching the line is because
There will still be reactants in the thing.
yes, right? But now let's say the reaction is evaporation, something like that, right?
Then there will be nothing left.
Will it touch the line?
Yes, good. But evaporation is not a reaction. Here is,
Okay.
for your sake, please listen. If the moles drop down to 0, then obviously this mole graph will go down to 0. But what you might not be thinking of now is that this reaction is actually a reversible reaction. So this reaction will never reach a 0 mole. Because the more ammonia is formed, the more it will decompose to form hydrogen and nitrogen again. But that's not my point of discussion at this point in time. I don't want to discuss reversible reactions at this moment in time.
Okay, and then if you see toast, right, the moment it's toasted, right?
Yeah, you get non-reversible reactions. Yes?
So that one is not reversible, right?
Yeah.
So would that be the type of reaction that touches the graph at the bottom?
I don't know if you will toast everything to nothing, to no bread, to just charcoal. I don't know. But that's not your worry. Your worry is to be able to read the graph and to interpret the information. So on a concentration time graph, or on a mole time graph, or on a volume time graph, the rate will be the gradient of the tangent to that point. Okay? And on a rate graph, you're actually plotting the rate values. Then, when the reaction has stopped, the rate will be 0. That is what you need to understand. You need to be able to see the difference between the two graphs.
Will the rate graph always go to 0?
If the reaction has time to stop, yes. But if it's a reversible reaction, it never stops. So it can never go to 0.
None?
Yes.
How can you have 0 moles or something?
If everything is used up.
But you still have a product.
Yes, but this is the reaction rate for the reactants making product. So this is the rate of the reaction of the reactants. This is what happens to the reactants.
So you're not looking at the whole reaction, only the first half.
Just the hydrogen reacting with the nitrogen, that part of the reaction will slow down.
So you're just going to keep looking at the reactants, and eventually when the reactants can't react, then you say those are the reactants and those reactants can't make anything.
They stopped. I'm going to do the next one now. You see, I numbered that one 1.
Ma'am?
What's on the side?
That side is just the words, the amount of reactants used per second. So that is this one. Or the amount of products formed per second is the next one, number 2, is coming. So this is how the reactants change. So this is the mole of the reactants and how they change. Next graph is the moles of the products and how they will change. Okay, can I go to that next slide?
So ma'am, if this was the one for the reactants, why does it have a negative?
Because these gradients of the tangents are negative. They slope down. From left to right, they slope down. So the gradient of the tangent is negative, but you don't want a negative answer for rate. That's why this value here, the change in moles, will be negative. Because you've got a smaller number of moles minus a bigger number of moles. So that value will be negative. To get your rate as a positive value, you minus the change in the moles, or you minus the change in the volume. Can I move to the next graph now? Okay. So graph number 2 is where we look at the change in the moles of the product. So what did you start off with? No. We took hydrogen and we mixed it with nitrogen. How much ammonia was there at the start? 0. So we start at 0. Your mole of, so this is the mole of the NH3 in this case. So you start off with nothing. And how is the rate of formation of ammonia at the start of the reaction? Does it form fast in the beginning, or does it form slowly in the beginning? Yes, I know the graph is like this, but it forms fast in the beginning. So this is the amount of ammonia we start off with, and initially, because the reaction starts off fast, the moles of ammonia will increase fast. So the tangent here is a high tangent. The graph, the formation of ammonia, the rate of the formation of ammonia is high initially. But as the reaction slows down, what happens to the rate of the formation of ammonia? It slows down and it will become 0. There where the graph flattens out, the reaction has stopped. So now this reaction tells you the change in the moles gets slower and slower. Here the reaction gradient of the graph is positive. So the rate
That's why this one.
of the production of ammonia can be determined by the change in moles over time. And that's, the negative has disappeared from the equation now because the gradient is positive. Now, whether we look at the hydrogen reacting with the nitrogen, or whether we look at the product's formation, the ammonia's formation, what will happen to the rate graph? It will look exactly the same. It starts off with a high rate, so the gradient here is high. That's the gradient of the graph, is high. And slowly but surely it becomes 0. The rate of the graph.
Then if the graph of the other one was what was going down as well.
Yeah. It means that the rate of the reaction slows down as the chemicals are used up.
Regardless of whether it's
The product you are looking at or the reactants you're looking at, the rate of the reaction slows down. The rate of the reaction between the reactants, between the hydrogen and the nitrogen, slows down because it's used up. And for that reason, the rate of formation of ammonia will also slow down.
So
So
when
then, because the previous slide, the rate was also going like that because of
Yeah?
right?
Because the gradient of the graph slows down, it gets smaller and smaller until it becomes naught.
because either way it still slows down.
Yes, whether you look at the moles of the reactants, which will be decreasing, the moles of the reactants is decreasing, whether you look at that reaction, or whether you look at the moles of the product increasing, the reaction slows down.
Ma'am, I'm kind of confused with these graphs, because when we're doing these ones of the when we're doing these ones of the products, right? Are we going from products to reactants, or like what's actually going on? 'Cause-
We're going from reactant to product.
Okay, so then the previous ones we were also going from reactant to products.
Yes.
Mind you,
But
what are the graphs?
we were looking at what happens to the moles of the hydrogen and the nitrogen. We were looking at the moles of nitrogen and hydrogen.
Okay,
It will decrease.
yeah.
But it will decrease slower and slower. As less hydrogen and nitrogen is in the container, the reaction will slow down.
That's calm. Then the next one, why the graph, like what are we looking at? Why is the graph now?
This one,
Yeah.
this graph, we're looking at the production of the ammonia. What will happen to the moles of ammonia as it is produced?
Oh.
It will increase. But it will increase slower and slower and slower. That's why the gradients of the tangents are less and less steep.
Okay. Thank you. Okay.
You're welcome. Sorry, Marcus. I have to hear what other people say, and if you talk in between, I can't hear. What did you want to say? Lilo, are you okay? Good. Rachel, are you okay? All right. Good. So, to conclude, on my next slide, you could be looking at the volume as well. Must I wait? So we want to use the collision theory to explain the factors that affects the rate of reactions. So I've got it all written out on the slides, so you could write it from there, but I want it to grow here. What is the collision theory saying?
A reaction will only take place if the particles
Collide.
There must be collisions
With sufficient energy
and
With
the
the
correct
correct
orientation.
orientation to cause a rearrangement of atoms.
Look at you guys.
Reading.
collisions
What we wrote
with
down.
sufficient
Energy
energy
orientation.
and
and orientation.
Correct.
So, correct orientation.
Now we spelled orientation wrong.
Alright, it's not the last thing I will spell wrong, that I can promise you. For effective
Rearrangement.
Of atom.
reaction. So these three things, or these 4 points if you want to say it, collision, energy, orientation, effective rearrangement, or effective collisions, we need to now use this in explaining the rates, the factors affecting rates. So can I go there now? Which factor must I explain first?
not the nature, the surface area.
Surface area.
And then the temperature.
Slow down.
Why would you jump instead of the order?
Nature. We did nature also.
So the state of division, if the state of division is increased, the surface area increases. Okay? If the surface area increases, there will be more collisions between the reactants. The energy of the collisions, the energy of the particles will be constant, but there will be more collisions. And the chances are that there will be more collisions with the correct orientation in the same period of time. There will be more effective collisions per unit time. I can't say direct proportionality because it will depend on the reagents involved. So I can't say there's a direct proportionality. So if the state of division is increased, the surface area will be increased, so there will be more contact between the reactants, there will be more chance of correct orientation and effective collisions. So, the greater the state of division, the more collisions will take place per unit time, but also the more collisions with the correct orientation will take place. Please don't copy this because you copied it from there. Correct orientation, so there will be the more the chance of effective collisions. Per unit time. Okay, next is concentration. So what can we say about a concentration? The higher the concentration, the more particles of reactant will be present. So there will be more collisions between the particles. Because there are more particles, there will be more collisions between the particles. So there will be more chance of collisions with the correct orientation. That is why the reaction will take place faster. There will be more effective collisions per unit time. So we're going to go to those slides now.
Yes, it was on school property in Scotland, so someone told me.
Still closest.
Just look at them and see that they have the same description with you.
And it's just going to cause more damage.
So when you could say in the test that explain in terms of the collision theory each one of these factors.
This thing with the correct orientation is creeping in the past 2 years, where they want you to stress that the orientation, there will be more collisions with the right orientation. It wasn't like that years ago, but they are stressing that in the last 2 years. So if you have more collisions per unit time, there will be more collisions with the correct orientation per unit time. So there is a greater chance for effective collisions.
At the right orientation in
Pardon? So temperature is easy. To me, it's always easier. If you increase the temperature, you increase the kinetic energy. There will be more collisions. More collisions with higher energy per unit time. That will lead to more effective collisions. So here, it's the energy of the particles that change. Because they are moving faster, they will collide more often. There will be more collisions with the correct orientation at a higher energy, and that leads to a faster reaction rate because of the increased energy.